Welcome to the recording of the webinar Current Challenges for Modern Hydraulic Systems. My name is Tobias Dohmen and I'm the innovation team leader at HYDAG Mobile Hydraulic. I've been with HYDAG for almost 4 years. However, let's start with our webinar, and I want to begin with a quote. Albert Einstein once said, "In the middle of difficulty lies opportunity." This quote perfectly captures the essence of what I want to discuss today with you. Challenges are not obstacles, they are chances. Chances to growth, chances for new solutions, and chances for innovation. Efficiency, noise, and complexity. Just 3 keywords that can be mentioned in context of challenges facing modern hydraulic systems. Let's take a step back and look at the technical, ecological, and social trends that determine the requirements of your machines. We can identify 3 megatrends: digitalization, decarbonization, and demographics. A wide range of trends and challenges can be identified around these megatrends. A megatrend such as digitalization influences countless trends, from software-defined machine to legislation, generating new challenges. One example is cybersecurity. The megatrend of decarbonization is obviously shaping technological change and represents a major transformation in the mobile machinery industry. Finally, the megatrends of democratic change, which is related to the development of new machines, and on the other hand, it's a motivation, for example, for mobile automation. After this introduction, I want to start with the first topic of today, efficiency. I want to start with a question. Do you know the load spectrum of your machine? I know that's a difficult question because there are so many ways your machine can be used. There are so many influences, starting from the driver, and ends up with the question of the working task of your machine. But if you can say yes, great, because that has been laid the groundwork for my second question. Do you know which losses occur in your machine? We will see later where these questions bring us. I want to start with the multi-level approach for energy-efficient hydraulic. On the first level, the component and design level. On this level, we have different solutions, for example, parts and body solution, and floor-optimized cartridge valves, and of course, pump with high efficiency. This solution will help to improve the efficiency, but they will not help you to systematically prevent losses in your machine. Systematic avoidance of losses can be achieved at the functional or system architecture level of your hydraulic system. The greatest potential can be found in new hydraulic architectures, but they also represent the biggest change in your machines and go hand in hand with an increased complexity of your machine. This webinar focuses on functions and the operating strategy and gives an outlook to new hydraulic architectures. Mobile working machines are characterized by a wide range of load collectives, depending on the machine, its application, and even the driver. Here are a few examples. On the one hand, the crawler excavator, which is more or less a stationary application. And on the other hand, there's a dumper, which is, in terms of its job, a driving machine for high time share of driving and low time share of working hydraulic functions. In between, application like the wheel loader or the telehandler. Looking at the machines and their use, one might get an idea that both have comparable load spectrums. However, if we look a little bit deeper in the literature, we can find load spectrums for the working hydraulic function of this machine. And now you can see that the working hydraulic or the load spectrum for the working hydraulic looks totally different. One example is the standby operation, which is for the telehandler much higher than for the wheel loader. The difference is also clear in terms of time share in the peak power and nominal power. The difference shows that the telehandler is used as a transport machine, while the wheel loader is used more for a rehandling operation on a construction site. Conclusion of this slide is that there is no one-fits-all solution. So now we get a little bit deeper into the hydraulic system and try to understand which losses occur in your system. But we start with the good news for you. If you are thinking about electrification and replacing the combustion engine, you will increase the efficiency of your machine due to the bad efficiency of a combustion engine, which is equal or lower than 40%. On the other hand, the electric drive, which with an efficiency of 90% of a right working range. So, is this the answer to the question how we can increase the efficiency of our machine? That's it? In my opinion, no. There's still a need for further energy savings on your machine to do the same job as before. That brings us to the question, where do the losses in the hydraulic system occur? The following illustration of an exemplary qualitative illustration of a Sankar diagram helps to explain this. The input energy, the 100%, is shown on the far left. At the end, the hydraulic output power of the main control valve, short MCV, is the power required to the job. This power is independent of efficiency and depends only on the machine and its working task. Between output power and input power, there are losses. On the one hand, throttling losses, and on the other hand, transforming losses, which occur by transforming electric power into hydraulic power. The throttling losses depends on operation strategy, load collective, parallel movements of different hydraulic consumers, pilot oil supply, etc. pp. The transforming losses depends on operation strategy of the electrohydraulic supply unit, the load collective of your machine as well, and of course the efficiency of the different components, that means pumps, motors, inverters and so on. Some of them can be influenced by technology, for example the operation strategy. You choose operation strategy for your machine, for example a constant flow system or a flow on demand system. Some of them are machine and application specific and depends on the load spectrum. For example, do you have parallel movements in your machine? It really depends on which machine doing which job. For me, the key to increase the efficiency in your hydraulic system is always to avoid throttling losses. There are two types of throttling losses. The first, throttling losses due to the pump delivers too much flow. That means more flow than the hydraulic actuators or the different function of your machines are needed. Second, throttling losses due to parallel movement of different function in a single pump system. In this diagram, we can see both types of throttling losses. These throttling losses due to the operation strategy of your pump, of your electrohydraulic system, because your pump always delivers the same amount of flow independent of the flow demand. And of course, throttling losses due to parallel movements, in this case of 3 different functions at 3 different pressure levels. Throttling losses strongly depends on the application, time share at peak power and so on. Flow on demand is the first step to reduce throttling losses in your system. Throttling losses, I mean the first type of throttling losses due to the operation strategy of your machine. These diagrams show the efficiency of a constant flow system these efficiency maps takes into account the efficiency of inverter, motor, pump, and so on. So it really is related to input electric energy on the DC bus and the output power which is used at the MCV. The red area is the area of high efficiency and the blue area is the area of low efficiency. We compare a constant flow system and a flow on demand system with a state-of-the-art load sensing pump. But first we look at the constant flow system. It's a fixed displacement pump at a fixed speed. That means the flow is independent of the flow demand. The pump delivers always the same amount of flow. On the other hand, we can see the variable displacement pump. The input speed of the pump is also constant. And we are changing the output flow of the pump by changing the swivel angle of the pump. That means the pump only delivers the amount of flow which is needed by the different functions of your machines. And now you can see in these diagrams which show the pressure and over the flow demand. And the colors shows you the efficiency at the different operation points. Some example, for example, at moderate flow demand, we can explain the losses in this diagram. The major losses occur due to the throttling losses because the pump always deliver the same amount of flow. On the right side, for the variable displacement pump, we can see that we are saving a lot of energy due to the fact that we are having a flow on demand system. That means only the flow which is needed is delivered by the pump. Okay, one key to increase the efficiency of your electrolytic supply in your electrified machine is, of course, flow on demand. But that's not a new information to you, because variable displacement pumps are state-of-the-art. One sentence to the throttling losses which occur in the system. We now see we have a single pump supply for your different function, and if you operate, in this case, 3 different functions at the same time at a different pressure level, we have also throttling losses due to the fact that we have just one pump system. In electrified machines, we have a new degree of freedom. The speed variable drives enables new solutions to increase efficiency and reduce the noise on the other hand. So, with the speed variable drive, we are able to build a flow on demand system with a fixed displacement pump. How we do this? We are changing the speed of the pump independently of the flow demand. That means if there is a high flow demand, we increase the speed. If there is a low flow demand, we decrease the speed. And you can see the efficiency map of a flow on demand system with a speed variable flow on demand system compared with a load sensing pump at a constant speed. You can see that we are reaching the same high efficiency or even higher. For one example, for an increased efficiency, we can see it at a moderate flow demand. We increase the efficiency of the electrohydraulic supply. But there's a second solution. Now we can use both degrees of freedoms, the speed and the swivel angle of the pump. That means independency of the flow demand and the pressure, we are able to swivel out the pump and increase the speed at the same time. And we can see the effect on the efficiency map. We increase the efficiency, especially at low flow demand and moderate flow demand, and we increase the areas of high efficiency. In a HiDAC world, we call our product which enable the speed variable flow on demand system HYDAC EcoPack Plus. The HYDAC EcoPack Plus is an enabler to use the advantages of the electric drive in an easy way. For me, the biggest advantage for the speed variable displacement pump is that we now are able to realize hydraulic power management. That means with increased pressure on a fixed displacement pump, the torque also increases. In fact, the speed variable drive of the electric machine is limited by torque. With the variable displacement pump, we are able to limit the torque by swiveling back at higher pressure and increase the speed at the same time to deliver the same amount of flow which is needed in this point. Now we will compare the different operating strategy for electrohydraulic supply units for two different applications, the telehandler and the wheel loader. The load spectrum of the working hydraulic from literature is shown on the far left. We also know the efficiency map of the constant flow supply unit. And now we are putting the load spectrum and cover it over the efficiency map of our electrohydraulic supply unit. And now we are able to give an average power or an energy consumption for example, 1 hour operation. We can calculate it based on the working hydraulic spectrum and the efficiency map. Of course, the working hydraulic spectrum, it's from literature. It's the best what I have found in literature, because if you're looking in the operation point other, you can see this field goes above the whole flow spectrum and above the whole pressure spectrum. That means we can also increase the accuracy of our calculation, of our assumption, if we have more information about the load spectrum of the machine. So, however, we set the energy, the DC energy for this machine with this supply unit at 100%. And now we are looking at the flow on demand system with variable displacement pump. Also the efficiency map that you already know, and put the load collective on it. And now you can see that the energy consumption of your electrohydraulic supply decreased drastically. Now you don't need 100% energy, just 42% for the telehandler and 54% for your wheel loader. That means you have increased the efficiency flow on demand system drastically. And on the other hand, you avoid throttling losses. Between 100% and the 42% are only throttling losses due to the supply strategy, the operating strategy. Now we came to the point that we will optimize the operation strategy with the speed variable drive. And our two solutions for a fixed displacement pump and for a variable displacement pump, and also of course with the degree of freedom of speed variability. We can decrease the energy consumption for the telehandler. That means for the speed variable drive, we just need 37% of the energy instead of 100%. And for the wheel loader, we can optimize the system by 2% or about 2%. We will later see which effect we can see on the noise level. Just a brief explanation of the HYDAC EcoPack Plus and 2 sentences. The idea behind is a pre-validated system that our customers can use the advantages of electric drive in an easy way. The EcoPack Plus is a pre-developed system. More on this later in this webinar. Due to the fact that we have a lot of different machines out there, you remember there's not one fits all solution. We can realize various configuration possibilities with the EcoPack Plus, starting with a single pump, a double pump for optimized standby. On the other hand, a double pump to downsize the electric drive. And of course, what I have shown on the last slide, the variable displacement pump in combination with speed variable drive, which enable to use the speed and the displacement of the pump as degree of freedom to increase or to optimize efficiency and noise. These different configurations make it possible to respond to the specific requirements of different machines. Now we are moving forward to another important aspect in the system architecture. We have now discussed the advantages of flow on demand. What we have not addressed is the general system architecture. Flow on demand in a closed center load sensing system is state of the art, of course. One example to realize the closed center load sensing is our LX3 or LX6 family of pre-compensated load sensing valves. Advantage of the load sensing system is the demand feedback due to the load sensing signal and the good controllability for the machine operator. The good controllability is achieved by two characteristics of these valves. The first one is that the flow depends only on valve actuation. The second one is the flow is independent of pressure due to the different compensator inside the load sensing valve. Another advantage is the interchangeability between the electric drive, featuring the speed variable flow on demand system, for example, and the traditional combustion engine with a load sensing pump. This allows electric and conventional machines to share the same platform. On the other hand, we still have many machines, especially in the compact range, with an open center system. The main difference in context of flow on demand for an open center system is there's no flow demand feedback. And of course, the pressure build-up depends on the center flow. The key word here is controllability, which makes it difficult for the machine operator to control and regulate the flow. I would like to briefly explain the last point in more detail. The illustration depicts a schematic of an open center hydraulic system. We have a center metering orifice and we have a metering orifice for the function. As the spool actuation increases, the inlet metering orifice opens, that's this one, allowing more flow to the function, while the center metering orifice, that's this one, restricting the flow through the center path and causing a pressure buildup until the load pressure is reached in the center and the check valve opens and the cylinder movement starts. Due to the fact that the pressure buildup in the center affects the start of the cylinder movement, there is high dependency on center flow. This effect is shown in the following diagram. That means we have on the one hand different pressure or the center pressure for two different center flows over spool actuation, and we can see the flow area over spool actuation for the center metering orifice. So for example, for a center flow of 40 liters per minute, we are reaching quickly the first, with the pressure buildup in the system, we are reaching the lower pressure load of load 1. If we increase the pressure up to this limit, the cylinder movements will start. The cylinder movements for a cylinder with a higher load will start later with a higher spool actuation. But now we look at the point if we're decreasing the center flow because we want to realize some energy savings, and this is working by reducing the center flow. Now we can see on the second curve here for 10 liters per minute center flow that there is more or less no difference between the starting point for cylinder movement for the high and for the lower load. That's the reason why we also call the open center system load sensitive. We have asked ourselves, can we get an open center system ready for flow on demand? And the answer is yes. Therefore, we develop more or less a special spool which enabled us to decrease the center flow and also have a good controllability for the operator. We will see this on the next slide. Second solution, what we did is that we develop a negative flow control plug, NFC plug, and these plugs gives us a demand feedback which enable us to control to realize flow on demand system, for example, with the Hydrac EcoPack Plus. Now what I mentioned before, two diagrams. I will briefly explain it. In the first diagram, we see the pressure in the center over the spool actuation. For a standard spool, that's the gray one, and the yellow one is the negative flow control spool, which is optimized for a lower center flow to realize a flow on demand system. And what we are seeing for the NFC spool is that we have a nice pressure buildup over spool actuation instead of the standard spool. On the right-hand diagram, we can see the speed of the speed variable flow on demand system over over spool actuation. And now you can see the increased resolution, what also will increase the controllability for the machine operator. Because for the standard spool, we have more or less a switching valve. In the end, you control the speed. By a hydraulic system, you control the flow. So the area of the spool actuation is very small. With the NFC spool, we increased this area by a factor of 3. And this helps us to increase the controllability of your machine. And also save energy with a flow on demand system, also for open center systems. Another way to reduce throttling losses, especially in compact machines, is the Hydrac Eco switch. For cost reason, some machines are electrified, but still using the hydrostatic drive. The speed of the drive is determined either by the driver or by the hydrostatic drive. Accordingly, there is no degree of freedom for the variable speed flow on demand with constant pump. With the Eco switch, we offer a solution for small machine without electronic, sensors and software. It works with open center system, closed center system, and of course, closed center load sensing system. The idea of the Eco switch is to use a double pump instead of a single pump for the working hydraulic functions that we can see here on the slide. Instead of one single pump to supply the working hydraulic functions, we're using two pumps. One pump we are able to switching into low pressure bypass at a low flow demand. We measure the flow demand of the system with the Hydrac Eco switch control block. That means the control block is able to measure the flow demand, and in high flow demand we are switching the second pump to the system, and in low flow demand we are switching the second pump stage into low pressure bypass. We have also some measurements to see how we increase the efficiency of your machine. In the first diagram we see the flow of the high pressure carryover for a reference machine with a 16 cc single pump. The high pressure carryover flow is the flow from the open center valve, which is not needed, so that's the amount of flow which is not used. And of course occur or causes throttling losses in your systems. And we compare it with our EcoSwitch solution with a 6 cc pump and a 10 cc pump. We are able to switching the 10 cc pump into low pressure bypass at low flow demand. And now what we are seeing is that we reduce the amount of flow at the high pressure carryover for one working task of a machine up to 60%. And this brings us to the second diagram, the electric power consumption of the machine without and with EcoSwitch. And we can see that we can save nearly 2.5 kilowatts, which is for a small machine like the machine we did these measurements with, it's more or less 25% of the battery capacity of the machine. So for small machine and also for bigger machines, for example for the auxiliary drives, this is a solution. On the other hand, it works with both drive technologies. That means because it's independent of the speed variability of the electric drive, you can also use it by traditional combustion engine or of course with the electric drive. We have now discussed the advantages of flow and demand and how we can avoid throttling losses due to the fact that the pump delivers too much flow. Anyway, avoiding throttling losses caused by parallel movements of different functions requires a more fundamental change at the hydraulic architecture level. One possible solution is the pressure level splitting achieved by using two independent hydraulic circuits. You know very well which functions are operated at the same time, and you know the pressure level. And now we are saying, for example, function A and B have more or less the same pressure. We put them in one hydraulic circuit, and we have a second hydraulic circuit for the third function. For example, in this case, a hydraulic motor. And because now we have two independent hydraulic circuits, we are able to avoid throttling losses between the pressure level of the pressure A and B and with the third function. On the other hand, we have in our mind a displacement controlled actuator. That means in your machine or in some machines we have the possibility to recuperate energy by lowering some loads. That means we have two hydraulic circuits. One is more or less traditional, and a second hydraulic circuit with a displacement control actuator. And now we are able, on the one hand, to avoid throttling losses between the functions, and during lowering the load we can get the energy back and recuperate energy. That means over the whole cycle of the machine, the input energy will decrease. And of course, we have in our mind a peak shaving system. The peak shaving system enables downsizing of the drive components, that means motor and inverter, or shifting the operation points of the drive with higher efficiency. In this diagram, there's the output energy shown over time, and we have time periods with a high power demand, and we have time periods with a low power demand. The idea is now, in time periods of low power demand, we are recharging an accumulator and using this energy in high power demand time periods and discharging the accumulator. That means we are now decreasing the peak power of our drive because we cutting the peaks. The following diagram shows the operating point spread of the drive without peak shaving and with a peak shaving for an 80-ton excavator. This was a simulation study for a dig-a-dump cycle. The operation point shifted course by the peak shaving system. You can clearly see this because we have one, more or less the main operation point is at 60 kilowatt. And we get rid of these power peaks. Benefits are downsizing of motor inverter and also that bring down cost and weight. We can gain some efficiency advantages by shifting the operation point, for example, on the combustion engine, and of course reduce peak loads, and this decreases the load stress on the components as well. Before we move on to the next section, let's briefly summarize the key insights we have discussed so far. In general, the key to high efficiency is to avoid throttling losses. Therefore, I have shown you different solutions. On the one hand, the High-Like Echo switch for smaller machines, but we have some solutions on a function level to optimize the electric hydraulic supply unit, because the speed variable drive enables new solutions to increase efficiency on one hand and reduce the noise on the other hand. And this is what I capture with the overhead of speed variable operation strategy. If we want further increase the efficiency of our machines, I give an outlook about different changes in the machine which affects the architecture level. One example is peak shaving or two hydraulic circuits, or the possibility to recuperate energy. If you are interested in evaluating energy savings potential of your current hydraulic system or innovative architecture such as pressure splitting or displacement controlled functions, feel free to reach out. Contact us to evaluate your system or to look deeper into future-ready solutions. Let's now turn our attention to the next topic: how we can reduce noise emission and enhancing comfort. In hydraulic systems, three types of sounds can differ: structure-borne, airborne, and fluid-borne sound. The sound types propagate in their corresponding media and interact at the phase boundaries where they are covered into each other. In hydraulic systems, the interaction between fluid and structure-borne sound within the system, as well as the conversion of structure-borne sound into airborne sound at the system boundaries, are relevant. Fluid-borne noise can propagate through other hydraulic components and thus lead to airborne noise at locations outside of the pump. Physically, airborne sound is a longitudinal wave propagating in the carrier medium air. The wave propagation causes a pressure fluctuation around the static ambient pressure. The human hearing is able to perceive pressure fluctuation in a range between 20 micropascal and 200 pascal, in a frequency range between 40 Hz and 20 kHz. The human hearing is able to perceive pressure fluctuation in a range between 20 micropascal and 200 pascal in a frequency range between 40 and 20 kHz. The sound pressure level is calculated according to the shown equation from the effective sound pressure in relation to a reference sound pressure P0. For airborne sound, the reference is 20 micropascal. It's equivalent to the human hearing threshold. The sound pressure level is expressed in decibel. This diagram shows the equal loudness curves, also called isophones, and illustrates the frequency-dependent perception of a sound, which is shown how our hearing varies across the frequency spectrum. The perceived loudness remains equal along a curve. And what you can see is that at low frequencies, the sound pressure level for the same loudness perception increases. The A weighting of the sound pressure level already takes this into account. That means at lower frequency, the sound pressure level is weighted lower as at higher frequencies. You can see this here. Why we need new metrics such as loudness or sharpness? Psychoacoustic and its metrics are not new. Psychoacoustic has been used for a long time in automotive industry or for consumer goods. However, its application to hydraulic components and systems has been quite uncommon up to date. As part of my research at the Institute, I was able to gain my first experience in this field. For me, the biggest advantages is on the one hand that psychoacoustic metrics are allocated to a perceptions, for example loudness. Loudness corresponds to perceived loudness of a sound. The loudness calculation considering the sound pressure level, the frequency of the sound, and also masking effects. Sharpness corresponds to the perception of high-frequency sound components. And there are much more, for example roughness. But for today, we want to focus on loudness. On the other hand, they have a linear scale. That's a big advantage of the psychoacoustic metrics. That means a noise of a loudness of 10 zone is twice as loud as a noise with 5 zone, but only half as loud as a noise with a loudness of 20 zone. I would like to explain this in an example from literature. And these graphs shows the distribution of a sound pressure level for an internal gear pump and axial piston pump and a sound of 1 kHz. These three sounds have the same sound pressure level. One note at this point, for the internal gear pump and the axial piston pump, they have different operation point. It's not important to understand these graphs, but it's important to keep that in mind. Now we are calculating the specific loudness for these three different sounds. And the second diagram shows the specific loudness over the tonality. The tonality is linked to the frequency of the sound. Also, we can see how the loudness is calculated by the specific loudness. That means the loudness is the area above or under these curves. And what we now see is that the sound of 1 kHz has a lower loudness as, for example, the internal gear pump and the axial piston pump. And there's a factor of 3 behind them. That means the perceived loudness of the pumps are 3 times higher than that of the synthetic sound. Even all have the same sound pressure level. With that in mind, let's turn our attention to the impact of the operating strategy on noise and sound perception. We know these applications, the telehandler and the wheel loader. We also have seen the load spectrum as well. And now here is the sound pressure map for 3 different supply units. Constant flow operating strategy, which means we have always the same speed. And what you can see is that the sound pressure only depends on the pressure level of the system. With the variable displacement pump, but at constant speed, you can see that the pressure has a higher influence on the sound pressure level as the flow demand. And of course, for a speed variable flow and demand system, we increase the speed with an increasing flow demand, and this leads to a higher sound pressure level, or the sound pressure level increased with a higher flow demand. So we can see the efficiency map is a sound pressure map. It looks different for the different types of electrohydraulic supply units. And now we are putting the load spectrum over it, and now we are able to calculate an average sound pressure level. On one hand, and on the other hand, we are able to calculate an average loudness to put a number on this type of electrohydraulic supply unit. For the telehandler, we calculate a sound pressure level of 70 dBA and a loudness of 22 zone. For the variable displacement pump, we decreases the sound pressure level by 10 dBA and decrease the loudness to 14 zone. With our speed variable flow and demand system, we are able to optimize the efficiency on the one hand, and on the other hand, we are decreasing the noise. That means we can calculate a sound pressure level of 54 dBA for the telehandler, and for the wheel loader, due to the higher nominal and peak power operation points in the load spectrum, the sound pressure level is a little bit higher as for the telehandler. We can calculate at 59 dBA. But on the other hand, this is really interesting. We can achieve for the telehandler a loudness of 9 zone. That means, in fact, that we decreases the perceived loudness 35% up to 60% for the telehandler. And for the wheel loader, we lower the perceived loudness from 24 to up to 40%. That's a lot. Because I'm often asked what influence has a pump on the noise, I would like to briefly discuss the following diagram. Above, we show the A-weighted sound pressure level as well as the loudness over speed for 2 different pumps, silent pump and a super silent pump at a constant load pressure of 200 bar. Now we can see that the sound pressure level increases drastically with speed. It's the same for the silent and also for the super silent pump. At 500 RPM, the difference is about 15 dBA. But how does it affect this the perception? The difference in loudness is about factor 2. That means this difference is factor 2. That means the super silent pump is half as loud as the silent pump. On these diagrams, I show for a constant speed. The the sound pressure level and the loudness over an increasing pressure. And what you can see is, and what I want to show to you is that the gradient of the sound pressure level and the loudness is higher on the diagram above. That means the speed has a higher influence on the noise of the pump as the pressure. We saw this clearly on the last slide. At the end, selection of a pump is always a compromise between efficiency, noise and cost, but also taking into account, for example, speed and pressure limits and so on. Another way to reduce noise in the system is a high-duct silencer. We remember fluid-borne noise can propagate through other hydraulic components, and this leads to airborne noise at location outside of the pump. The high-duct silencer helps to reduce pressure pulsation caused by the pump. Therefore, we are using a high-duct multiple Helmholtz resonator concepts. One resonate volume with multiply necks for broadband performance. You can see that the pressure fluctuation on the inside is higher than on the outside. These reduced pulsation or pressure pulsation emitted by the displacement unit is a source of noise. That means with reduction of this pressure fluctuation, we are reducing the noise emission in the hydraulic system. The big advantages of the high-duct silencer is there's no installation of moving parts, no gas connection, and no maintenance. We have universal standard silencer or customized solutions. I have an example today for a machine. It's a traditional machine, to be honest, with silencer and without silencer. The difference between both are about 4 dBA. But the bigger difference we can see in the frequency spectrum. You can see that the pressure amplitudes are reduced at a certain frequency. At this point, I'd like to highlight the key takeaways up to now. Loudness allows a direct conclusion to made on a human hearing perception. And I show how the speed variable operation strategy of an electrohydraulic supply can reduce the perceived loudness on your machine up to 60%. Now we came to the topic of mastering complexity in a world of technological change. Let me start with a video. 20 years ago, a video was released that has become a timeless classic. The video shows Steve Ballmer, former CEO of Microsoft in the early 20s. He's talking about the key to industry transformation, and his key to success was developer. And the question to you is this a statement still relevant? But now we just look into the video.
Developers. The key to .NET, the key to industry transformation, the key to success is developers, 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 developers. Developers, 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 developers. Yes!
Developers, developers, developers. What do you think? Is this statement still relevant? Again, this question. But now I want to briefly explain the Carnot model. The Carnot model is a framework used to focus on customer needs by different product features based on how they affect the customer satisfaction. It divides features into 3 categories: basic attributes, performance attributes, and excited attributes. Basic attributes are must-have features for your machine. If these features are missing, customers are dissatisfied, but having them doesn't increase satisfaction. Performance attributes. The more of these features your machine have, the better. Satisfaction increases linearly with performance. And last but not least, the excited attributes. Unexpected feature that surprise customer. They create a high satisfaction but are not missed if absent. Over time, customer expectation shifts. We all know this from our passenger cars. Today, excited attributes become tomorrow's performance attributes or even basic expectations. The Carnot model helps to track these changes to ensure products stay relevant and competitive. How could a Carnot model look for mobile machinery in context of hydraulic features? A small note on this point, the model shown does not claim to be complete. So just look into the excited attributes of yesterday. Maybe we can identify electrohydraulic pilot-operated main control valves. And today, there may be performance attributes. And tomorrow, they become basic attributes. Perhaps even more exciting than looking at the machine yesterday and today, it's looking at machines of the future. What do I expect to be exciting attributes in the near future? For example, multi-pump systems, autonomous systems and autonomous functions, or hydraulic systems that supports autonomous functions, and brake-by-wire and steer-by-wire. And there are more. And in the far future, hydraulic systems special made to support autonomous machines. To be honest, I don't know. What do you think? However, it has become obviously that machines, including hydraulic features, will be continue increase defined by software, and the complexity of their function will increase. Let's return to the topic of developers. You remember? The current situation in Germany looks like this. Germany has more people than ever before. It's unclear in which direction we will move in the future, and there are different models for this. However, it's also a fact that in the next 12 years, approximately 30 million people will reach retirement age, and only a few can currently fill this gap. When looking at the situation for engineers, unfortunately, it becomes even worse. On the one hand, there's an increasing demand due to experienced engineers retiring and new complex tasks emerging. On the other hand, less and less people are starting and successfully completing studies in science, technology, engineering, and mathematics subjects. What is our solution at HYDAC? Instead of developing everything from the scratch, we want to use low-code or no-code solution. We remember that we want to develop our machine quickly with minimal number of developers. In terms of systems and software development, our goal is to use a modular approach with certified components. One approach is to use topic-specific subsystems or software libraries. We call them also toolboxes. I'm often asked what a subsystem is and what can I imagine under it. Here's a graphical illustration. You purchase a topic-specific subsystem, for example, a steering system. You receive a package with sensors, control unit, with pre-installed software and actuators and so on. This subsystem is designed for a specific machine function and can be integrated into your machine. The entire product is certified, ready for integration, It contains the complete functionality and can be configured via a service tool. In this context, when you have a control unit but not program it, you only have to adjust parameter. That's what we call no-code solution. Here's a possible landscape of HiDAC subsystems, toolboxes and solutions. The overview covers a wide spectrum of what HiDAC can offer to you. While my background is hydraulic system, I'm excited to share highlights from across our portfolio. We can find, of course, solutions for e-mobility like our e-kits. We have solutions for steering functions, also steering functions for trailers, for suspension systems, and so on. You can't find your suitable subsystem? Ask about adaptation of an existing subsystem, or start a customized development project with pre-developed software solutions. Today, I want to briefly highlight two subsystems from HiDAC. The application software VSPC, that stands for Variable Speed Pump Control as part of the HiDAC EcoPack Plus, and the HiDAC Ground Control for field sprayer application. We have already seen the advantages of the variable speed flow on demand in terms of efficiency and noise. I have also already mentioned the various configuration possibility of the EcoPack Plus, which make it possible to respond to the specific requirements of different machines. Here are 3 examples of different configuration possibility for low voltage applications up to 96 volt and on the other hand high voltage application up to 800 volt. Again, the idea behind the EcoPack Plus as pre-validated system is that our customer can use the advantages of the electric drive in an easy way. It only requires an enable signal to start. To meet this requirement, we have implemented additional features on top on the speed variable flow on demand. For example, soft start and soft stop feature, a power management and an error management. For example, a limpo mode and a derating function to prevent the drive of overheating. Alongside the main function, speed variable flow on demand. The second subsystem approach I like to highlight here has nothing to do with electrification, to be honest. Nevertheless, I like to briefly mention it as it demonstrates the advantage of the no-code approach. Brief description of the function. Field sprayer have a very long boom structure. You can see it in this picture here. The HiDAC Ground Control Plus controls the lift and the tilt axis. And of course are handling the right and the left structure. The system includes the hydraulics, the sensors and the control of the application software. Short, everything you need to implement this function on your machine. The big advantages I want to highlight here is that we reduce the complexity on one hand for the machine manufacturer and we increase the speed to market. And that's important in some machine areas to increase market share as well. So, because with less development costs, you can see it here, you can get faster into a market and at the end you create a higher market share. Before we move on, let's quickly recap the key points so far. We start with developers. Then we move on to the Carnot model to explain why the machines become more and more complex. In this context, I present the Carnot model for mobile machinery in the context of hydraulic features in the future. I expect that multi-pump systems, autonomous functions, brake-by-wire and steer-by-wire become an exciting attribute in the near future. But the question is, what do you think? Our approach to master complexity is to use topic-specific subsystems or software toolboxes. I showed you two examples for HiDAC subsystems, the EcoPack Plus and the HiDAC Ground Control Plus. Autonomous functions as excited attributes are a good crossover to our last topic, ready for automation. The topic of autonomous function has been on our minds at HiDAC for quite some time. Thanks to the interdisciplinary nature of this, the interplay of hydraulic, software and sensor technology in connection with different machines, it's a perfectly suitable playground for us at HiDAC. In 2022, we launched a development project to answer the following question: what is the best architecture of electronic, sensor and hydraulics to realize automational functions on a machine? Can I achieve an assistant working function with components that are used in ongoing project? And last but not least, what has to be changed from existing machines? Our answer is the HiDAC excavator. We have equipped this complete machine with HiDAC technology, starting with the main control valve, angle sensors, tilt sensors, position sensor, and almost 50 pressure sensors. The large number of sensors can be explained by the fact that we want to compare the accuracy and the dynamics of the different sensor technologies. The result? We developed software toolboxes. More on this on the next slide. And we also identify key components. Perhaps even more important, we understand the challenges related to mobile automation because we had to overcome them by ourselves. With this knowledge, we can support our customers. As already mentioned, the interdisciplinarity nature of this. This means the interplay of hydraulic, software and sensor technology in connection with different machines. We took this into account when we developing our mobile equipment automation toolbox. The core of the mobile equipment automation toolbox is an open kinematic chain, which enables us to use one approach for different machine kinematics. The kinematic calculates the necessary movement of different machine functions. In an excavator, for example, it's the movement of the boom stick and bucket cylinder. The kinematic calculates based on, of course, operation inputs. That means someone has to tell the machine who tasks to perform and, if necessary, how quickly the machine should perform it. And of course, the sensor inputs. I say it's the eye of the machine, which monitors the movement of the different machine functions, but more on the sensor technology later. The various actors are controlled as an output of the kinematics. That means we still have hydraulics to control the movements. That means we have some input interfaces, operator and sensors, and an output interface which communicate with the hydraulic system. And with this in our mind, we can imagine that the hydraulic have to be very accurate, have a high accuracy and good dynamic and so on. This brings us to the electromechanical spool actuation of our LX3 and LX6 family with the ICU. The advantages of the ICU are the reduced number of necessary I/Os of the vehicle control unit. because now on the machine more and more sensors are needed to measure the movement of the machine. With the ICU, just one connector for the whole MCV are needed. That's also an advantage because it simplifies the cable harness on your machine. The ICU also can increase the efficiency of your system because with the electromechanical spool actuation, we can get rid of the pilot oil and also from the pilot oil supply. The ICU enables valve diagnostic and error detection due to CAN communications, and this enables enhanced safety concepts. But for mobile automations, most important is the high position accuracy due to the high number of increments over the spool stroke and the high position accuracy without hysteresis. That means we have a feed-forward control on our ICU, which enables us to have a very high accuracy on the one hand, and on the other hand, a very high dynamic of the spool actuation. This improves assistance systems and automation functions in your machine. But last but not least, the eye of the machine. Sensors are the key to automation. Therefore, we have developed and tested our excavator sensors for inclination, linear position, angle, and pressure. Each sensor has its own advantages and disadvantages, for example in terms of installation, accuracy and dynamics and so on. It makes sense to consult our expert to select the right sensor for your specific application. Before we finish this webinar, I'd like to highlight the key takeaways from today. At the beginning of this webinar, I painted this dark picture of a mobile working machine surrounded by technological, environmental and social megatrends. Over the past 90 minutes, we have addressed many of this, far more than just efficiency, noise and complexity. They were of course the main focus of this webinar. One example is the HiDAC no-code approach. This approach helps a new machine generation which differs in many ways in terms of software functionality. The keyword of course is software-defined machine and therefore is linked to increased complexity in machine control. These challenges must be mastered in the context of short time to market and aging workforce. We remember developers. Applying this approach to products, the HiDAC EcoPack Plus shows how you can increase the efficiency and of your electrified machine through an optimized operating strategy and reduce noise emission as another keyword as well. I hope I have been able to give you an idea how HiDAC can help you with your transformation. If you are not curious about how much energy your machine could be saved, or if you want to be part of the developing of the next generation of hydraulic system, let's talk. Let's shape the future of hydraulics together. At the webinar, we asked our customers 3 questions, and these are the results. We asked our customers which topic related to modern hydraulic system interests you the most. And 69% say they are interested in energy efficient solution. The second question was, in which areas of hydraulic would you like to see more innovation? And the most people say they want to see innovation in the functional level of your machine. And the third question was, which system architecture would you like to test or to learn about? And 41% want to learn or want to test a displacement controlled system to realize a recuperation. Thank you for everybody who joined this on the survey. And I think it's very interesting results we can work on to increase the efficiency of your machine. Now I would like to thank you that you are listening to our webinar. Thank you very much for your interest.